for accepting my registration here. I'm quite glad to talk to you about some new directions that we have been taking in our work. So I do work with quite a few subjects related to foundations in terms of quantum information theory and also applications in the general quantum technology. But today I will talk about those two specific directions, which is related to quantum walks and quantum simulation, and together with quantum optimization algorithms. Okay, so the central part of my talk, I will talk to you about this paper, which is we put back in 2025 in the archive, so you can check that. And the second part, I will talk about another paper that is actually an extension of that in a nice way. Okay, so what is a minimal spanning tree that we are going to talk about? So let's suppose that I have a graph, an undirected graph, G, composed by V, which is the set of vertices, and E is the set of edges, and each will be represented by an unordered pair of vertices, U and V, that belongs to this edge set associated with a specific cost. So this is the cost related to every single edge here. When we have that, the minimal spanning tree is defined by this new tree here that span the vertices in G while minimizing the total cost. So quite soon you see a very nice problem that you recognize as a very practical thing. But in a general way, let's suppose that I have a graph like that, so with many vertices and edges, but we have also the weights here. So we actually want to go to the situation where we have the summation of the specific and local weights to be the minimal. So we will have something like that. So this is the minimal spanning tree. So just to check about the applications and also the complexity here. So for example, if we don't have any restrictions, I will talk about that in a minute, we have classical algorithms which are quite good for that, which is the Kruskal and Prim. So without restrictions, this belongs to the class P. And for example, the applications is when you talk about the energy distribution in general. Okay, so if you distribute the power energy. But when we have restrictions, meaning, for example, that we have some paths that cannot be coupled, or even when we have degeneracy in terms of those weights, we have different kinds of algorithms, which is called the modified Kruskal, modified Prim, and colony that can be used in general. But this problem is now not a very easy problem. It's actually an NP hard. And actually when N, these restrictions is actually 2, not larger than 2, then this is even harder in general. So this is an NP complete problem. So for example, is related to delivery logistics in general, okay? So so we will check a different way to tackle this problem. So this is essentially what I will talk about and try to convince you that this is a different way and actually is quantum inspired, is not specifically quantum, but is a nice way to check those algorithms and to modify. Essentially, we could in principle modify all of those previous algorithms, including some quantum elements here. Okay. So just for you to know the relevance of this kind of investigation, so the minimal spanning tree is related to many practical things. So it goes from telecom and fiber networks, power grids, transportation pipelines, urban infrastructure, logistics, and so on. I will not talk about all of those, but it's essentially a very nice problem because it's related to many things that we recognize as quite important. So, for example, you have seen the traveling salesman person. So this is a very important problem in general, and this is a subclass of this minimal spanning tree problem. Okay, so let's move on. I think I have it here. So there is the standard way to solve this in terms of quantum mechanics is going for a cubical formulation. So cubical formulations, what you have to do is to write down all this is a quadratic problem. The quadratic comes here from all those Boolean variables that are described here. And when I have that, so I have actually many terms here. One is related to a single root that we are actually trying to minimize or maximize depending on the problem that we are actually tackling. And we have other terms that are related to uniqueness of the depth of each vertex and so on. We have many terms, and one of those is quite important, is related to the cost. So everybody knows, I think that in this community here, that it's possible to transform these Boolean variables in terms of i's in Hamiltonian. So if we do this transformation here, going from X to actually the operator, the Pauli operator Z, and then we actually can write down this as an analyzing Hamiltonian. This is quite nice because there are many, many problems, NP hard, NP complete problems that can be solved in that way. There is a very nice paper. I think this is a really nice paper that covers many of those problems. If you want to see how to write down the Hamiltonian for a specific cubical formulation of an optimization problem, then you go to that direction. But everybody that starts working with this kind of problems and go for a quantum computer to trying to solve this faces with a problem. It's quite, it's quite hard to get the exact numbers of qubits that you would need to attack some irrelevant problem. So, for example, it involves, so just in terms of a general, it involves around of something like n to 3 binary variables and n to 5 interactions between nodes. But the worst thing, it's quite disappointing in terms of a general way. So if, for example, if you go to a simple applications in terms of communication networks, and let's suppose that I want to attack a problem with just 100 number of vertices. I would have to use in that formulation, because it also, for each bit of classical information, or if vertex, or if each edge that you have to add 1 qubit. But when you add also the constraints, you have to add another qubit and so on. So this is scale up quite fastly. So for simulating, for attacking a problem of 100 vertices, you have to use 10,000 qubits. For communication networks, and supposing, for example, the internet or even social networks, for attacking a problem with 175 millions, you would have this enormous number of qubits that, of course, we don't have it at hand. And even for a smaller situation, for example, electrical grids, just to check if it works, we would need something that we don't have at our hand, which is 900 qubits. When I talk about qubits, I'm talking about logical qubits. I'm not talking about physical qubits here. So in principle, there is no noise here, okay? So, of course, this is quite disappointing. Everybody that starts working with that thinks that quantum mechanics or quantum computing will solve optimization problem, but then quite fastly, as soon as you start simulating that and going for the simulation, for example, in terms of Qiskit, and going for the IBM quantum computer, so you get disappointed because the results are quite bad in terms of when you have noise, but also what you can simulate at your own computer, it's really small. Okay, so possibly is it possible to go to another directions? No, yeah, I'm here just to talk about a different direction. But for that, we have to go to a shift in terms of paradigm. So for that, I will have to assume a simple hypothesis that has been working so far. Quite possibly there are situations that this doesn't go as easy as I'm telling you. But the hypothesis is that given a fully connected graph, the minimum spanning tree corresponds to the path of highest cumulative transition probabilities. This is actually the same hypothesis that you do in terms of the Kruskal. Kruskal is very simple. So let's suppose that you are in this vertex and you want to go to the minimal one. What you do is just to follow the minimal path here. And then when you reach this vertex, you just check which one is the one with the minimal weight in terms of the edges, and then you go to that one. So at the end of the calculation, you expect that your minimal spanning tree corresponds to that path that you followed, which corresponds to the highest cumulative transition probabilities. The difference here is that they don't talk about probabilities. They talk, in terms of the Kruskal algorithm, they talk about the weight of those edges. Okay, so I will transform that in terms of probabilities because this is what we try to understand in physics, and we are more comfortable of talking about. So for doing that, I will actually just do something which is quite is very nice in terms of resources, of use of resources, and which is just a simple binary codification in terms of those numbers. So for example, I just go for a binary codification of all those numbers of these our nodes of our graph, and just map this into a transition problem of those possible states. So this is actually quite good for saving resources. So if the number of vertices are multiple to, the number of qubits is actually, it increases to the logarithm of n. So this is good, okay? So if not, just go the logarithm of n base 2 plus 1, and it's also good, okay? All right. So how do we do, to probe the system in a better way? So for that, we use the property of random walks when you implement in terms of a quantum system. So I think that you know already, but let's suppose that I have two people here. One is Alice. So Alice here, and Alice follows a simple path by just flipping a coin and go to the directions that is the coin indicates. If it's heads or if it's tails, it goes to one or other directions, and at the end it ends in a different place. But Bob, our other person goes, it has, for example, a quantum coin, and since the coin can live in a superposition, it goes simultaneously through all of those paths. So this is actually quite well understood as a very good resource for search algorithms in general. And if you want to see just in general, you can go to these references here. So why we are employing this quantum walk? Because quantum walk in general can probe. Let's suppose that I have a graph like that, and if I implement a continuous walk in a graph, in a general graph, I have the ability to probe this graph quite fastly. So it's well known that continuous walk, they propagate over this network very fastly. All right, so for doing this continuous walk, so I'm not using a coin, I'm just using a continuous walk. The way to do that is just to write down this Hamiltonian, which is related, it's like a tight binding Hamiltonian, related to the energy of each site, and also to the transition energy of those of neighboring sites in general. So when I have this connection, all of those graphs, all of those edges represented here with their weights, I just transform to that problem, and then we move on to our calculation. So I actually, remember that I assume that my minimal spanning tree is related to the cumulative, the smaller cumulative weight in terms of the transition. But I also assume something else. I assume that the cumulative weight is related to the inverse of the probability of transition. So this is I need you also to assume. So this is the way to attack this problem relating to the quantum walk. So so this is another hypothesis. So giving a fully connected graph, the minimal spanning tree corresponds to this path of highest cumulative transition probability, but also I assume that this probability is given by the inverse of the weight of each one of the edges. But so I have a way to calculate that in general. So this is I assume this possibility. And we have, behind all of that, we have the physical basis for that. We assume actually that we are talking about a Markov chain. So if it's not, we have a way to correct that. So it's not a problem. But I'm actually hiding all the details for you. And in general, so if we go with the minimal spanning tree without restrictions, so this is the procedure. So we actually just go with the evolution with the quantum walk starting from the initial node and go to the other ones. And when we reach that a specific one, which we find it's the minimum, we calculate the transition probabilities, and then we go to the next one from that one, and so on until we find. I think it's not going. No, okay. Until we find the minimal one, okay? Just to have a list of transition probabilities, and I have to consult this list and go to the final solution for my problem. Okay, so this is the very simple problem. So if you compare this, for example, with the Kruskal, so this is the Kruskal I showed to you before, how do we calculate. So this is the comparison on how the quantum walk goes compared with the Kruskal. So the quantum walk actually copy almost everything that the Kruskal does, so it's not better, but I'm not expecting it to be better because this is a P problem right now. The problem comes when we assume that we have restrictions, and I will show to you what will happen. Okay, so for calculating that, I have I hide some calculations before. So this is the transition probability in general. So what you have. So what we assume is I like to call it like a quantum Kruskal, because what we do is exactly what the Kruskal algorithm does, but we insert this quantum walk in the beginning of each time step. So with that, this is the algorithm without restrictions. So what happens with the system? And let's see, for example, how it compares with the other algorithms. So for example, remember that I talked to you about this communication network with just 100 vertices. I needed 10,000 qubits if we wanted, for example, to use the best algorithm for doing doing quantum annealing. But for that one, if we want to use our procedure, we just need 7 qubits. Sorry. If you want to go to a larger situation, for example, a communication network with 107,000 million nodes, which is very large, I assume that we will never have a computer as large as this, in terms of qubits. But here I just need 28 qubits. I know that quite possibly you guys don't believe that this can be solved. But you have to check the paper, and I promise you that I can talk to you and try to convince you in a general way. And if we go to general problems, so for example, a very important problem related to national scale electrical grids. So we need something around 10 to 8, qubits. This is quite hard to solve, but here I just need 14 qubits. It's too good, to be true, isn't it? Okay, there is something behind. But here I'm talking about the situation without restrictions. So restrictions is a key problem. I don't have problem to solve that in my classical computer. I have good methods. There is something here that I will not talk about. This is the object of a different talk, but I think that this would be, you guys can appreciate that. Because if we calculate, for example, the entropy of this guy, the Shannon entropy, versus the total weight, so this guy here, so we have many points, but notice this line, what is pointing. This point here corresponds to the minimal spanning tree. The minimal spanning tree corresponds to this, so this is the weight, but also this guy is the largest amount of entropy that I have. So there is a principle in general, in statistics and also in information theory, that if you maximize entropy, you find something nice, for example, related to the distribution. You can actually talk about everything that you talk about quantum statistics or mechanical statistics, even classical, you can do that just by maximizing the entropy. But there is something else that we know that comes from physics, that physicists, they love that, which is related to the minimal action, for example. So minimal action, so let's suppose that I go back to that graph. So many of you, I think, are physicists, so you can follow that. So this is related to the action. So when I have a minimal spanning tree, in a sense, if I talk about the probability, if the edge weight is related to the inverse of probability, this is actually related, to the minimal action in some point. So actually, what I'm doing here is somewhat relating the maximal entropy to the minimal action in this graph. Okay, so this is actually quite important in terms of general things. This was proven in general for the situation where we have, again, when we have a Markov, we have a Markov chain, and some results related to that, and some other problems also related to this action theory can be consulted in those papers, which are in the archive as well. So this is quite nice because we recover relativistic distributions just based on this principle of maximal entropy related to the minimal, or actually I should say, extremize the action of the problem. Okay. Let's go back to our problem. So if I insert these restrictions, there is also a problem because I will need more qubits if I go to the situation where I try to solve this by a Hamiltonian. So if I use it in the Hamiltonian, I have the same problem that I have when I try to solve in a Kubo formulation. I have the constraints introduced in the Hamiltonian. They will increase the number of qubits, and so I have a problem when I want to implement. I also can insert it specifically in the Hamiltonian, but it's a little bit tricky how to do that without increasing the number of qubits. But I also can do a data query. Data query is almost what I have been doing. Like we could use, for example, I have a list of transition probabilities. I could use at the end some Grover algorithm to go over the classical search algorithm, but I don't need that because what I get in terms of economy of resources is already good enough for me. Okay, so what we do is just going for that situation, for that options in terms of data queries. So I do everything that I did before, but at the end, for example, if I have a restriction, so I assume here that my restriction is related to the situation where I have degeneracy of two transition points. So for example, let's suppose that I reach this vertex here. What I do, if those transition probabilities are the same, so I have to choose one. So this is actually quite hard, gets quite hard to solve because this gets to the NP complete problem, NP hard problem, is a kind of NP hard problem. All right. So after that, I just have to select those transitions that are not allowed. And at the end, what we have is a better solution for this problem. So here is finally my final result for this minimal spanning tree problem. So I have a numerical calculations of many of those possible solutions. One is the greedy, prim, Kruskal, and also we have a exact solution, which is this brown one. So when you compare to what you want to find, what is the best solution, the minimal solution should be this brown one. But if you compare to our method here, this is the blue dot one, what you see is that in the most of the situations, it's not always, you reach actually a very good number here. It's very close. It's closer than the other algorithms that you can find. So it's better. So the important lesson here, it's economic in terms of resources, very economic, and it's better than the classical versions of that. So the algorithm 2 goes like that. So I just have a minimal addition here, which is related to this to this loop that I have to go to include my my restrictions. Okay, so in general, I have this map. So I will not cover, I will not talk about all of this, but of course, I'm talking about the scalability of this problem and the complexity in general. But you also can compare, other properties. For example, if you want to scale the number in terms of the number of qubits, or if you want to see the complexity related to the QUBO problem formulation, or even with the Fowler formulation for the D-wave kind of solution, you can go to this map here. There are many advantages. Of course, there are other disadvantages as well, but I'm not talking about that. And this is it. Okay. So there's another problem, which is actually an extension of that it's quite important, and it's related to the minimal vertex cover. 3 minutes, that's enough. Okay, so this is quite important. For example, when we go to network security, epidemic control, infrastructure maintenance, robotics, and so on. So swarm of drones, for example, if you want to cover a certain area, how many drones can I use? Of course, I wanted to use a smaller number as possible. And there is a very important problem that we are solving with this kind of problem solution, which is how you place, for example, sensors in oil platform. So an oil platform is something like that. So there are many ones. But you have sensors of oil or gas leakage placed all around this platform in general. So you don't want to have many, in general, you don't have an easy access to these points, okay? So you cannot just fix it as you wish. You have to do that from time to time when you have access to these points of this platform. But what you'd want to do is to use the smallest number possible of sensors to cover all this, all this area of this platform, for example. So this can be used, this minimal vertex cover can be used like that. I don't go through all the details, but I have an additional detail here, but because I just use quantum walk again to attack this problem. But also, when I actually go to a specific, this is specific for this minimal vertex cover problem, but the solution is almost similar to what I told you before. When we go to a specific vertex, I have to eliminate my previous path because now I want to cover a new one, a new area, and then I go on and follow all of those paths, and at the end I end up with this minimal vertex cover. Okay, So if you compare our solution with all the available classical solutions, our is best in general situations, and moreover is not dependent on the kind of graph that we are attacking. This is a problem that all the classical solutions, they are sensible to this. If you change from kind to kind of graphs, you have actually a different behavior, but our solution is actually good. And if you want to see the results of this, is here. Okay, so I will finish with this showing this graph. So this heat map is related to how good the algorithm is. So the closer it is to 1, it is better. So this is our version, quantum. So you can see that the number, even though everybody here is close to 1 in a sense, but there are ones that are closer, and ours is closer, so it's better. Okay? All right, so the conclusion, the general conclusion is that quantum heuristics can be a viable alternative for reducing quantum resource with suboptimal solutions in NP-hard problems. Suboptimal because it's not the optimal one, as I showed you. There is an exact solution that we cannot reach that result for many times. There are many points here, but I leave you to read that, and if you have questions, I will be happy to talk about. Thank you.
So we have time just for a short question.
No question.
No question. So thank you again.
Thank you.